A sudden engine bay fire can destroy a $40,000 car in under 3 minutes, and the culprit is often a tiny $9 piece of rubber hose. Most drivers assume fuel lines last forever as long as they aren't dripping liquid petrol onto the driveway. But inside your engine bay, a silent chemical process is destroying those lines right now without leaving a single drop on the pavement. By the end of this video, you will see the microscopic trigger that turns flexible rubber into brittle glass, and the simple 30-second pinch test that could save your car from total destruction. Fuel system fires account for thousands of vehicle total losses every single year, yet nearly all of them begin with invisible micro-cracks. Today, modern fuel injection systems operate at pressures up to 2,000 pounds per square inch, turning tiny hose floors into high-pressure aerosol sprayers. We are going to analyze the exact thermal heat cycles that bake your fuel lines every time you turn off your ignition. You will also see why modern ethanol fuel blends are actively eroding these lines from the inside out while you drive. To understand why fuel lines fail, you first need to look at how synthetic rubber hoses are constructed. A standard automotive fuel line isn't just a simple hollow rubber tube, it is a multi-layered composite structure. The inner liner is specifically formulated using nitrile rubber to withstand aggressive liquid hydrocarbons without dissolving. Surrounding this liner is a high-tensile fabric reinforcement braid designed to contain internal fluid pressure. Finally, an outer synthetic rubber jacket shields the internal layers from oil, heat, and environmental exposure. The primary enemy destroying rubber fuel lines under your hood is a physical process called thermal cycling. Every time you drive your car, the engine bay warms up to over 200 degrees Fahrenheit. When you park and turn off the engine, all cooling airflow instantly stops while the burning metal engine block radiates immense residual heat. This phenomenon, known as heat soak, causes ambient air temperature around the fuel rail to spike violently. Over hundreds of driving trips, these intense heat spikes continuously bake the hose material. During intense heat soak, crucial chemical compounds called plasticizers begin to evaporate out of the rubber compound. Plasticizers are specialized additive molecules embedded into synthetic rubber to keep the polymer chains flexible and resilient. As heat drives these volatile molecules out of the hose, the synthetic rubber permanently hardens and loses its elastic memory. This structural degradation is what mechanics refer to as dry rot. Once plasticizers are gone, the flexible rubber tube transforms into a rigid, fragile material prone to surface cracking. While thermal heat cooks the hose from the engine, ozone gas launches an aggressive attack on the exterior surface. Electrical components like alternators, ignition coils, and electric cooling fan motors generate ground-level ozone inside the tight engine compartment. Ozone molecules attack the double chemical bonds within unsaturated rubber polymers, snapping those molecular chains apart. This chemical breakdown manifests as deep, sharp cracks running perpendicular to the direction of stress along the outer hose jacket. It isn't just external factors causing damage, modern ethanol-blended gasoline attacks your fuel lines from within. Ethanol acts as a powerful solvent that gradually strips away protective oils from standard nitrile rubber linings. Furthermore, ethanol is highly hygroscopic, meaning it constantly pulls water moisture directly out of the surrounding air. This water and alcohol mixture turns acidic over time, corroding interior metal fittings and eroding inner rubber walls until the hose thins from the inside. Older carbureted fuel systems operated at modest pressures of just 4 to 7 pounds per square inch. Modern port and direct injection systems push fuel through lines at 40 to over 2,000 psi. When an aging rubber hose develops micro-cracks under high pressure, fuel does not merely drip out slowly. Instead, the high pressure forces liquid fuel through tiny cracks as a microscopic atomized aerosol mist. This airborne fuel fog is exponentially easier to ignite than a puddle of liquid gasoline. Mechanical vibration accelerates this degradation process every single mile you drive down the road. Your car's engine moves constantly on its rubber motor mounts during acceleration, gear changes, and idle vibrations. Fuel lines bridging the gap between the stationary vehicle chassis and the moving engine undergo continuous physical flexing. Over time, this repeated bending forces stress directly onto hardened, dry-rotted rubber sections near metal clamp connections. Eventually, the internal reinforcing fabric braid snaps, leaving only weakened outer rubber holding back pressure. Improper maintenance practices frequently create severe leak hazards during routine component replacements under the hood. Standard worm gear hose clamps apply uneven clamping forces and cut sharp edges into soft outer hose jackets when over-tightened. Professional fuel injection systems require constant tension spring clamps or smooth band fuel injection clamps that maintain uniform pressure through temperature shifts. Using the wrong clamp style pinches the hardened rubber, creating localized stress concentrations that rapidly develop into full structural splits. A fuel line leak rarely ignites from an open flame because open flames simply do not exist inside a running engine bay. Instead, atomized fuel mist sprays onto scorching hot exhaust manifolds or catalytic converters reaching over 1200 degrees Fahrenheit. Liquid gasoline requires a direct spark, but aerosolized fuel mist reaching auto-ignition temperature on red-hot metal ignites spontaneously without a spark. Once ignited, the electric fuel pump continues pumping gallons of fresh fuel directly into the fire until power is cut. Detecting compromised fuel lines before they burst requires a methodical inspection routine rather than a quick glance. Microcracks usually hide on the underside of hose bends or beneath protective heat sleeves where light rarely reaches. Utilizing a bright LED light and a small inspection mirror allows you to scan the full circumference of every fuel line. You must focus attention specifically where flexible rubber hoses press over hard metal barb fittings and high-stress crimp connections. Visual checks only reveal surface damage, so tactile testing is necessary to evaluate the internal integrity of the hose. With the engine completely cold and switched off, gently squeeze the hose along its entire length using your fingers. A healthy fuel line feels firm yet pliable, springing back to its original shape instantly without any cracking sounds. If the hose feels rock-hard, unyielding, spongy, or makes a faint crunching sound when flexed, the structural reinforcement is compromised. When replacing compromised fuel lines, upgrading to modern synthetic hose materials eliminates future dry rot issues entirely. Advanced vehicle builds utilize PTFE, or Teflon-lined, stainless steel braided hoses that are completely impervious to ethanol and ozone. Alternative fluorocarbon synthetic rubbers, commonly known as Vitorn, handle extreme engine bay temperatures up to 400 degrees Fahrenheit without degrading. Upgrading to these modern material standards ensures your fuel lines outlast the rest of the mechanical components. Establishing a preventative fuel system maintenance routine is essential for any vehicle over 7 years old. Inspect every accessible fuel hose during routine oil changes, looking for swelling, stiffness, or oily residues along the rubber surface. Ensure fuel lines are securely routed away from sharp metal edges, steering shafts, and unshielded exhaust components using proper mounting clips. Installing an automatic fuel pump inertia cutoff switch provides a crucial safety net by stopping fuel flow immediately during a severe impact. A thorough 5-minute fuel line inspection costs nothing, but ignoring dry-rotted hoses can lead to catastrophic vehicle loss. Understanding how heat soak, ozone gas, and ethanol fuels degrade synthetic rubber empowers you to spot failures early. Take a flashlight to your car's engine bay this weekend and perform the pinch test on every reachable hose line. Catching microscopic rubber cracking today is the single most effective way to prevent a sudden engine fire tomorrow.